NASA's own cameras can't agree if this comet is dead or alive. Imagine 2 security cameras watching the same street. On one screen, a car is a faint blur, almost not there. On the other, the same car looks bright and sharp, like a ghost with its headlights on full. Now, replace that street with the space around our sun and the car with an interstellar comet called 3I Atlas. One spacecraft says, "Relax." Another shows a clear, active streak cutting through the glare. Same object, same time window, 2 completely different stories. Tonight, you and I are opening that case together. By the end, you'll have to decide for yourself, is this just extreme geometry and harsh sunlight, or the most perfectly hidden visitor our solar system has seen so far? Let's start like investigators, not believers. That 3I tag means third interstellar object ever confirmed. Oumuamua was the first. 2I Borisov was the second. 3I Atlas is number 3 on the list. Fact: it is not born with our sun. It doesn't share our family cradle, like Pluto or Halley. It dives in from deep space at over 130,000 miles per hour, fast enough to loop around Earth in under 11 minutes, if you could bend its path into a circle. It curves once around the sun, and then it's gone on a hyperbolic path. No cozy orbit, no see you next century. We get one pass, one shot to measure it, argue about it, and maybe learn something before it fades back into the dark between stars. This is not a cute snowball. 3I Atlas carries the mass of a city-sized mountain. Some early estimates put it at hundreds of billions of tons. Picture a solid block, large enough to stand next to an entire skyline. Now push that block through space, faster than anything you've ever seen in a disaster movie. As it wrapped around the sun, it may have lost up to 13% of that mass. That means billions of tons of ice and dust ripped away in a single close pass. And yet, on some of our best cameras, that violence looks strangely quiet. Not a roaring comet tail filling the frame, but a pale, almost embarrassed smear. Fact: the physics is violent, but the images often look muted, almost like the sun turned the volume down right where our cameras are listening. Now we look at what 3I Atlas is made of. Most comets near the sun follow a simple rule. Water wakes up first. Ice warms, water vapor erupts, and you see strong water signatures in the spectrum. The light fingerprint. With 3I Atlas, something strange happened. Fact: observations showed carbon dioxide lines louder than water, CO₂ shouting, H2O whispering. There are natural options on the menu. Maybe it formed in a carbon-rich pocket of its original star-forming cloud. Maybe a thick, dusty crust locks water deeper down, while CO₂ escapes more easily through cracks. Weird? Yes. Impossible? No. But if you wanted a comet that passes every physics test while still leaving a weird fingerprint, starting with barely plausible chemistry, would be a clever way to get our attention without breaking any rules. Now, dust. Dust is where comets tell secrets. When sunlight hits comet dust, it doesn't just bounce back, it gets polarized. The light waves line up in a pattern. That pattern tells astronomers about grain size and shape. Fact: with 3I Atlas, the way light scattered and polarized didn't quite match our usual solar system categories. Still inside normal physics, but nudged toward the edge of what we're used to seeing. So, your case file now holds interstellar speed, one-time hyperbolic path, huge mass, big mass loss, odd CO2, heavy chemistry, unusual dust and light behavior. Every single one has a standard explanation. But when you stack them together, this object stops feeling like background noise and starts feeling like a deliberate pattern, drawn right on the edge of boring but natural. Our planets live in a thin disk called the planetary plane. Most of the interesting action, Mercury, Venus, Earth, Mars, Jupiter, sits close to that sheet. 3i Atlas doesn't cruise safely above or below it. It slices through it. Gravity alone can do this. Given enough random interstellar visitors, some will cut right through the crowded zone. But if you handed a careful navigator a model of our solar system and said, "Give me a path that maximizes the chance that any spacefaring species here will have to notice this visitor," you'd probably draw something very close to the line 3i Atlas actually took. Let's pause and count what's already on the board. Interstellar origin, one pass, no return, city mass scale, billions of tons lost, CO2 shouting, water whispering, unusual dust, a path that threads our own planetary plane. Every line is still inside what physics allows. But together they feel less like random dice rolls and more like someone pressed a thumb into our model of the solar system and said, "Try solving this one." Right now, if 0% is pure accident and 100% is deliberately designed pattern, where does your gut sit? Pick a number in your head, and if you're brave, drop it in the comments. Now, I want you to feel this as a timeline, not just a list of weird facts. Fact, exact dates and times come from official circulars and databases. We'll keep it simple here. Picture this as a crime board with string, but in space. On one night, survey teams spot a faint moving point. That doesn't fit the usual patterns. At first, it's just another entry in a long list. They mark it, file it, keep watching. Over the next nights, positions line up with a strange orbit. Numbers whisper, "This thing may not be from here." In group chats and email chains, no one writes interstellar yet. You never use the big word too early, but people start staying up late. They run extra fits, double-check code, rerun simulations, just to be sure they're not fooling themselves. A few days later, more data locks in. Orbital fits show this object isn't bound to the sun. Its path is not an ellipse. It's a hyperbola, the curve of a visitor that will not return. That's the moment the quiet word appears. Interstellar, fact. It gets tagged into the growing family. First, Oumuamua, then Borisov. Now this. Astronomers feel two emotions at once. One, excitement. This is a chance to measure another piece of another star's leftovers. Two, pressure. Interstellar means you don't get second chances. This is a once-only performance. Telescopes across the world start competing for time. Some win, some lose. Weather, schedules, funding, all the messy human stuff decide which parts of the story we get to keep. Next pin on our board, perihelion, closest approach to the sun. On that date, 3i Atlas dives into brutal sunlight. Solar radiation slams its surface, volatiles boil, dust jets erupt, billions of tons of material start to peel away. At the same time, our sensors are fighting for their lives. Near the sun, detectors risk getting flooded with light. You shorten exposures, tighten filters, and accept that your view will never be perfect. Fact, this is when SOHO and stereo get their key images. Later in the video, we'll put those two feeds side by side, and you'll see why they lit the argument on fire. For now, just pin this moment The day a mountain of interstellar rock tried to rip itself apart in a place where our cameras see worst. After perihelion, the story should be simple. The comet fades. The show is over. But with 3I Atlas, some signals say otherwise. Fact: radio and spectral data show continued signs of activity, what some astronomers call the comet's breath, even as its visible tail seems to collapse in some cameras. So on our timeline, we add 2 more pins: breath detected, chemistry and gas still active. Optical fade. Tail and coma look weaker than you'd expect for what's happening physically. This is where the quiet on screen, loud in data paradox starts to feel real. And this is where online rumors begin to wake up. Whenever reality leaves gaps, the internet fills them. Let's walk through a few myths that grew around 3I Atlas. First myth: it split in half and vanished. You'll see comments and posts saying the comet suddenly broke into 2 perfect pieces, then disappeared like a magic trick. Rumor. That's the emotional story. 2 chunks, then nothing. Reality. Some frames and light curves can look like a brightness dip or shape change. But so far, there is no confirmed measurement showing a clean, symmetric split into 2 long-lived fragments. Dust shells, rotation, and changing viewing angles can mimic that effect. Label for this myth: no evidence. 3I Atlas does not need to crack like a movie asteroid to be interesting. The real data is already strange enough. Second myth: 3I Atlas made a right-angle turn. You might have seen claims that the comet suddenly changed direction like a drone, as if it hit the brakes and turned a sharp corner. Rumor. That sounds like a steering event. Very dramatic. Reality. When you plot an orbit on different background star fields, or switch from heliocentric to geocentric views, the path can look like it bends sharply, even though the object's motion is smooth and curved. It's an issue of projection and reference frame, not a real stunt. No credible data set today shows a clean, 90-degree turn that breaks orbital mechanics. The path of 3I Atlas is weird enough without adding cartoon corners. Third myth: it pulsed like a machine with perfect timing. You'll sometimes read that the comet brightened and dimmed with clock-like precision, like a beacon turning on and off. Rumor. That kind of story makes it sound engineered. Reality. Comets do brighten and fade over time. Rotation, jets pointing toward or away from us, and changes in viewing angle can create patterns, but not with perfect, second-by-second regularity. Fact. If an object showed extremely precise, repeated pulses with no good physical reason, scientists would absolutely flag that as suspicious. But with 3I Atlas, we don't see that kind of clockwork pattern in the public light curves. Question for you. Before watching this, would you have believed the split in 2 or perfect pulses stories if you saw them in a comment? Yes or no, and why? Fourth myth: NASA is hiding the close-up images. Whenever a space story gets big, this one shows up. They must have better pictures they won't show us. Rumor. The idea is that crisp, detailed shots of 3I Atlas are locked in a vault somewhere. Reality. Most of what we know comes from telescopes not designed for close, pretty shots. SOHO and stereo were built to watch the sun, not to give us movie-level comet portraits. And when high-value data is taken by major facilities, it usually ends up in public archives, after a standard delay for calibration and research. There's no evidence today of sharp, secret close-ups being withheld from the public. 3I Atlas is frustrating because the cameras we do have were in the wrong places, not because someone is hiding a 4K glamour shot. Now, now that we've cleared out some myths, let's come back to the images that started this video. Two spacecraft, same time window, same interstellar visitor. SOHO's LASCO C3 shows a faint smear, almost like the show is over. Stereo A's HI1 shows a clearer streak, more like a comet still breathing. This is measured data, not rumor, not a YouTube thumbnail trick. In a few minutes, we'll break down why forward scattering, exposure choices, and viewing angle can make billions of tons of activity look quiet in one camera and obvious in another. But I don't want you to lose the emotional part. If you only had SOHO, you'd think almost dead. If you only had stereo, you'd think very alive. Same universe. Two truths on your screens. We'll come back and put them side by side with simple diagrams. For now, let that discomfort sit with you. Good science starts by trying to kill the mystery, so we give the boring explanation every chance to win. Near the sun, dust does not behave politely. If you look almost directly down the comet's tail, with the sun behind it, light scatters forward, away from your camera. That's called forward scattering. The dust and tail can be busy and violent in reality, but your camera is staring straight into the flashlight instead of watching it from the side. Rotate your angle a bit, and suddenly the same dust goes from barely there to wow, that's bright. For 3i Atlas, SOHO may simply have had the worst possible angle. Stereo may have had the better seat. This doesn't magic the mystery away, but it takes a big bite out of it. If that sounds like a cop-out, remember the scale. We're talking about billions of tons of material blown off this comet. The idea that camera angle alone can make that look anemic feels wrong in your gut, but that's exactly what forward scattering can do. It never cancels the physics. It cancels our view of physics from that one unlucky angle. Reality keeps happening. Dust still flies. Gas still vents. Our sensor just isn't sitting in the right place to feel it properly. So yes, it is absolutely possible for one instrument to see almost nothing, while another sees a clearly active comet. That's not evidence of a cover-up. It's a reminder that we designed our eyes for convenience and safety, not for extreme geometry near the sun. Now zoom out another step. 3i Atlas doesn't just expose one weird comet, it exposes a hole in how we watch the sky. Most big surveys avoid the bright region right next to the sun. Too much glare, too much scattered light, too much risk to the detectors. But those same twilight zones, just before sunrise, just after sunset, are exactly where fast interstellar visitors are most likely to slice through from our point of view. The places where the most interesting objects pass are also the places we deliberately look away from. 3i Atlas arrived in that awkward geometry almost like a polite sticky note on our cosmic fridge. Here, this part of your map still says, "Here be dragons." So here's your second uncomfortable question. If one interstellar comet can lose billions of tons of material right in front of us and still look half invisible from one angle, how many visitors like this have already cut through our twilight zone and left without ever being promoted from weird streak to object we name? One? A handful? Dozens? Hundreds? The honest answer is simple. We don't know. If you were watching from another star and you understood our survey habits better than we do, you would know exactly where to fly your messenger to stay beneath our attention. So what's your bet? Comment seen if you think we've caught most visitors, or missed if you think we're still half blind. Let's leave pictures for a moment and look at the numbers. Comets don't just follow pure gravity. As they warm up, gas jets off their surface. Tiny thrusters they never ordered. The push is small, millimeters per second, but over millions of kilometers. Those little kicks bend the path enough for careful instruments to notice. Scientists call this non-gravitational acceleration. Here's the key. It is completely natural. We see it in our own comets all the time. But if you want to test whether an object is possibly artificial, this is one of the first places you look. You ask, are the small pushes we see in the orbit consistent with what we can see coming off the object? Or are there extra nudges with no good physical source? If 3I Atlas showed a strong, clean, repeated push with no sign of outgassing, that would be a big red flag. So far, we don't see that kind of smoking gun. Orbit is one test. Light is another. If you want to know whether something might be artificial, you also look at light curve anomalies. Does it brighten and fade in strange, repeated patterns? Material fingerprints. Do spectra show elements or compounds that scream technology instead of rock and ice? Repeating timing. If it blinks or pulses with machine-like precision that natural physics can't explain, that's a big clue. Fact, 3I Atlas does not show clean, repeating, perfect pulses that force us to say, beacon. Its chemistry is odd, but still inside natural possibilities. If it had flash prime numbers in brightness, or shown a stable, exact repetition every few minutes with no good physical reason, we would not be calling it just a comet in any serious discussion. Now let's clearly mark this next part. Thought experiment, not a claim. Engineers have a word for something hidden inside something else. A Trojan on Earth. We've already flown small probes attached to asteroids and comets. Hardware wrapped in rock and ice. Stretch that idea. Imagine a completely natural outer shell, shaped by collisions, sunlight, dust and gas over eons. Inside that shell, a more regular core, dense, protected, maybe carrying instruments that only need to last for a short mission. From the outside, you run all your tests. Spectrum, light curve, non-gravitational pushes, and everything can still scream, comet. That's the unsettling part. If anyone out there ever decided to do this, the result would look almost exactly like a slightly weird natural object on paper. Here's the question. I've wrestled with myself. What scares you more? The idea that no one is out there, and these interstellar visitors are just rocks, or the idea that someone has already sent something this way, and we only notice because two cameras happen to disagree? If 3I Atlas is purely natural, it still exposes how narrow our vision is, how casually our instruments can erase billions of tons of real activity. If it ever turned out to be more than that, it wouldn't just change astronomy, it would change how we see ourselves. A young, noisy species that nearly missed its first proper hello. 3I Atlas is only the third interstellar visitor we've confirmed. There will be a 4I, a 5I, and more. So what do we do next time a stranger from another star dives toward our sun? Astronomers are already planning new all-sky surveys that scan deeper into twilight. Better space-based telescopes that don't fear the sun as much. Coordinated campaigns where multiple instruments, optical, radio, infrared, watch together from different angles. Maybe even cameras parked at special points like L1, or in Mars orbit, ready to catch the next visitor from a new vantage point. Next time, we might not be arguing over a faint streak. Next time, we might be debating a clear, detailed object that forces us to ask a harder question. Do we answer back? So let's put you in the control room. Imagine you run one observatory on Earth. You're told, we just spotted 4I, the next interstellar visitor. You only get one band, one main way to look at it for the first week. Where do you point your power? Do you go for visible light to get pictures people understand? Infrared, to see heat and buried ice. Radio, to listen for chemistry and maybe strange signals. Ultraviolet, to watch the violent end of molecules in sunlight. Comment with your pick, VIS, IR, radio, or UV, and tell us why. Because the truth is, the tools we build and the choices we make when the next visitor appears will decide whether future humans argue over rumors or over real hard data.